So this online video deals with the tutorial questions of and the quantum mechanical description of the electronic configuration of atoms. So the first question asks, when ultraviolet radiation of wavelength 58.4 nanometers from a helium lamp is directed on a sample of krypton, electrons are ejected with a speed of 1.59 megameters per second. Calculate the ionization energy of krypton. Now in this chapter we look at the calculation of ionization energies, but this is actually just an example of the photoelectric effect, and similar to one of the questions that appeared in your first class test. So for question 1, the photoelectric effect, the wavelength 58.4 nanometers and the speed 1.59 megameters per second, which is the speed of the ejected electrons. Now ionization energy is equal to the work function as defined in the first chapter. And remember we said if the photon has energy h nu and an electron is ejected, part of that is used for the work function, which in this case is ionization energy, to eject the electron, and the remaining energy is transferred to the electron as kinetic energy. So this is for the photon and that is for the electron. So don't mix up the two particles. So if you recall, for the photoelectric effect, the energy of the photon is equal to ionization energy or work function plus kinetic energy of the electron. So ionization energy is h nu minus that term. So we can just substitute the constants. And remember, we can substitute mu with c over lambda because we are given wavelength. Minus the second term, which I'm just going to write here, mass of an electron, which you will be given if it's not given in the data sheet, and the speed so if you calculate that, you can find the ionization energy of krypton. Second question, what is the orbital angular momentum of an electron in the orbitals 1s, 3s and 3d? Give the numbers of angular and radial nodes in each case. So in order to calculate the angular momentum, we use the following equation that is related to the angular momentum quantum number. Using that expression, the number of nodes are equal to n minus 1. The number of angular nodes are equal to the quantum number L, and the number of radial nodes equal to n minus L minus 1. So this is a piece of new information that we haven't seen before. So firstly, for a 1s orbital, n is 1, L is 0. So the angular momentum, which is J, will just be equal to 0, because L is 0. If you substitute it into that equation, which gives you J. Angular nodes, 0. Radial nodes, in this case also 0. Total nodes, also 0. For a 3s electron, L is 0, N is equal to 3. So the angular momentum is again 0. The total number of nodes is 2. Number of angular nodes is L, which is 0, and the radial nodes is N, which is 2, minus L is 0, minus 1 is 2, which makes sense because the 0 total number of nodes is 2, 0 angular nodes, so all the nodes must be radial nodes. C part, 3d electron, L is 2, N is 3, so angular momentum is equal to the square root of 6 h bar. Total number of nodes, n minus 1, which is 2. Angular nodes, equal to L is 2. Radial nodes is N is 3 minus 2 minus 1 is equal to 0. Question 3. Calculate the permitted values for J for a d electron and an f electron. So remember, to calculate J for a single electron, we will use the Clebsch-Gordon series, or we can just look at J as equal to L plus S or L minus S. So for a d electron, L would be 2, S is always equal to a half, so J is equal to L plus S, or J is equal to L minus S, 2 plus a half, or J is equal to 2 minus a half, which is equal to 5 over 2, or 3 over 2. And the second part for an F electron, L is 3, S is always a half, so J can be 3 plus a half, or 3 minus a half, which is 7 over 2, or 5 over 2. So those are the possible values for J for an F electron. Which of the following transitions are allowed in the normal electronic emission spectrum of an atom? And then a couple of transitions are given. First one, 2s to 1s. So remember, the rule that we have to use is that your change in angular momentum must be plus or minus 1, because that is the angular momentum of a photon. So for a 2s orbital, L is 0. For a 1s orbital, L is 0. So your change in L in this case is 0. So it's not plus or minus 1. So this is not allowed. So it's a forbidden transition. Second part of the question, a transition from 2p to 1s. So here your L is 1, there the L is 0, so the change in L is minus 1. To go from 1 to 0 you have to subtract 1. So this is definitely allowed according to that selection rule. Part C, 3D to 2P. In this case L is 2, L is 1, change in L is minus 1, so that would be allowed. And I just want to add one more example here. Let's say we had 3D to 2S, L is 2, L is 0, so your change in L would be minus 2, which would be forbidden. And then the next part of the question combines some of the concepts that we looked at when we discussed term symbols. So there was a paper in which some scientists attempted to determine the electron configuration of the ground state of an element called lawrencium, element 103. The two contending configurations are given there. First part of the question, write down the term symbols for each of these configurations and identify the lowest level within each configuration. Which level would be the lowest in energy according to a simple estimate of spin-orbit coupling? So we have two possible configurations. The first one looks like that. Let's call that configuration A. The second possible one which we call configuration B looks like that. And we want the term symbols for both of these. Now remember, when you determine or when you work at a term symbol, you only look at the unpaired electrons. So here we effectively have a closed shell. So we only have to consider that part. And the same for this configuration, that is closed, so we only have to look at that part. So only electrons outside closed shell. Okay, so let's look at the A configuration. We have a 7p1 electron. Now this is a simple case because we only have one electron. Remember that simplifies things. For that electron, L is equal to 1, S is always equal to a half. So because it's a one electron system, we can first work with the lowercase symbols. J is L plus S, J is L minus S. So it would be 3/2 or a half. If we want to determine the term symbols for a one electron system, we know that the following is true. L is equal to So the total orbital angular momentum is equal to the orbital angular momentum quantum number. The same goes for the total spin angular momentum. Is equal to that, is equal to a half. And J is equal to that. So J is equal to 3 over 2, or J is equal to a half. We also need the multiplicity, which is 2 times a half plus 1, which is equal to 2. So to write the term symbol, we need to find the symbol using L. So it's a P. It's split into 2 J values, 3 over 2.5, and the multiplicity is 2 in both cases. So there we have the term symbol for that A configuration. Question: which of those two has the lowest energy? Well, the one with the smallest J. So for that configuration, this term will have the lowest energy. Now let's do the same for the second configuration. Here we have to consider the 6d electron. So for the B configuration, we have 61. Again, it's a 1 electron system, so things are simple. L is equal to 2. S is equal to S is equal to a half. J is equal to J, and that could be L plus S or L minus S, which gives you a value of 3 over 2. Sorry, that would be 5 over 2, and this one would be 3 over 2. So our J is 3 over 2 or 5 over 2. Based on an L equal to 2, the symbol is D. It's split into 2 levels. So 5 over 2. And then multiplicity, 2 times a half plus 1 would be 2. So there we have the 2 terms. This one is the lowest in energy because it has the lowest J. Okay, so we've answered the first part of the question, which asks us to write down the term symbols for each of these configurations. And we've identified the lowest energy level within each configuration. So the last question is, which level would be the lowest in energy according to a simple estimate of spin-orbit coupling? So now we have to calculate the energies of the two. Well, we've got 4 levels, 4 terms. Which one has the lowest energy? Well, that one is definitely higher than this one, so it's either this one or that one. So which of those two has the lowest energy? So in order to calculate the energies of a term, we use the following equation. Okay, so for the A configuration, which is the 2p half configuration, the energy is half HCA, J is a half, L in this case is equal to 1, and S is always a half. And that gives you an answer of minus HCA. For the B configuration, which is this one, the lowest one of the B configuration of the possible 2, we will find that the energy is equal to that. So which of those two is the lowest? Well, that is lower than that. So the lowest energy is that one. So based on this calculation, it would seem that this is the lowest energy and that this is the most likely configuration. So based on that, one can say that this B configuration is, based on the knowledge that we have, the most probable configuration, electronic configuration for that specific atom.